In this episode, we are focusing on the part of the computer that quietly controls almost every other hardware decision, the motherboard, which many technicians also call the system board. New learners often picture it as just the big flat board that everything plugs into, but it is really the physical and electrical foundation that tells the rest of the system what can fit, what can connect, and what can work together reliably. A great many expensive support mistakes begin before a screwdriver ever touches the case, because someone assumes that any board will fit any case, accept any processor, or power any set of components as long as the plugs seem close enough. Once you understand form factors, built-in features, front panel connections, and the simple compatibility checks that technicians use before installing or ordering parts, the whole repair process becomes calmer, cheaper, and far less likely to turn into a return, a dead-on-arrival build, or a machine that powers on but never becomes dependable. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at Cyber.Me in the Bare Metal Study Guide series. A motherboard does two jobs at the same time, and beginners usually notice only one of them. The obvious job is physical because it gives the processor, memory, storage devices, expansion cards, cooling connections, and rear ports a place to live inside the system. The less obvious job is coordination, because the board provides the pathways, timing, power delivery, and control logic that allow all of those parts to communicate in an organized way instead of behaving like unrelated pieces of hardware. That is why technicians do not treat the board as a generic tray full of connectors, because once the board is wrong, everything around it becomes harder to choose, install, or troubleshoot. And even good parts can appear defective simply because they are being asked to work on a platform that does not support them properly. When a learner starts thinking of the motherboard as the traffic system and power map for the whole computer rather than just a large part in the middle, compatibility decisions begin to make far more sense, and installation work stops feeling random. One of the first compatibility ideas a technician learns is form factor, which is simply the size and layout standard that tells you how the board is shaped, where mounting points sit, and how the rear ports line up with the case opening. The most common desktop examples are Advanced Technology Extended, ATX, Micro Advanced Technology Extended, Micro ATX, and Mini Information Technology Extended, Mini ITX, and each one represents a different balance between physical size, expansion room, and building flexibility. An ATX board usually offers more space for expansion slots, headers, and connectors, while a smaller Micro ATX or Mini ITX board may fit more compact systems but leave less room for add-in hardware and internal cabling. That means the board is not chosen in isolation because the case has to support that form factor, the mounting pattern has to match, the rear connector area has to align, and the builder has to accept the trade-off between a smaller footprint and fewer options for future upgrades or easier hands-on servicing. After size, the next thing technicians evaluate is what the board already includes before any extra parts are added. Many boards provide built-in audio, network access, multiple storage connections, display outputs for supported processors, fan headers, and several universal serial bus (USB) connection options, which can save money and reduce the need for separate add-in cards. Some boards are designed for basic office systems and include only the features needed for common tasks, while others are built for heavier workloads and offer more ports, stronger power delivery, more high-speed storage options, or better support for multiple displays and additional peripherals. The important lesson for a beginner is that onboard features are not just marketing details, because every missing feature may require another purchase. Every extra feature may influence case space and cooling decisions, and every overlooked limitation can turn a simple installation into a frustrating discovery after the machine is already assembled and expected to work. Processor compatibility is one of the most common places where good intentions produce bad results, because a board and a processor can look related on paper while still being incompatible in practice. The board must support the correct central processing unit, CPU, socket, the right processor family, and the right firmware level, and technicians check all three because a physical fit alone does not guarantee that the system will start. A board may accept a chip of a certain shape, but still need a newer firmware version before it can recognize that specific generation, which is why experienced technicians never assume that a new processor will work simply because the socket seems to match. They also think about the heat and power needs of the processor, because a system board that can technically host a chip may still be a poor choice if the board design, the cooler clearance, or the case airflow cannot support stable long-term operation without random shutdowns or reduced reliability. Memory support creates a similar kind of trap for beginners, especially when they hear that memory is just memory and assume any stick will do. The board must support the right type of random access memory, RAM, the right number of modules, and a realistic capacity for the intended use. And technicians also consider how the slots are arranged so the memory can operate as efficiently as the platform allows. A board with 2 slots and a board with 4 slots may both run the system today, but they offer very different upgrade paths, and that difference matters when a user may need more memory later without throwing away perfectly good modules. Even before installation, a technician is thinking about whether the memory height will interfere with a large cooler, whether the board supports the planned speed well enough for stable use, and whether mixing unmatched modules might create behavior that looks like a motherboard failure when the real problem is poor memory planning from the start. Storage and expansion choices depend heavily on the board as well, and this is where many learners begin to realize how a small board decision can ripple across the entire build. A board may provide a certain number of storage connectors, a certain number of expansion slots, and a certain arrangement for fast solid-state drives, but the usable options can change depending on what other devices are already installed. Peripheral Component Interconnect Express (PCIe) slots differ in size, lane availability, and intended purpose, so a board that looks generous at first glance may still be a poor match for a system that needs a graphics card, extra storage, and another expansion device at the same time. The same logic applies to Serial Advanced Technology Attachment (SATA) ports and internal storage placement, because technicians know that a small office machine, a gaming system, and a workstation do not stress the motherboard in the same way. And choosing a board without enough room for the intended hardware often causes instability, bottlenecks, or unnecessary follow-up repairs. Power compatibility is another area where mistakes become expensive very quickly, because the system board depends on both the power supply and the case layout being correct. Most desktop boards expect a main board power connection and a separate processor power connection, and technicians verify those needs before installation instead of discovering halfway through the build that the power supply lacks the required connector or cable length. They also pay attention to where those power connectors sit on the board, because a connector placed near the top edge can become awkward in a cramped case, and poor cable routing can block airflow, stress connectors, or make later service work harder than it needs to be. A system that shuts off unexpectedly, refuses to start, or behaves inconsistently under load may lead a beginner to blame the board itself. But technicians know that weak power planning, missing connectors, and physically strained cables can produce symptoms that look like a bad motherboard when the deeper issue is support hardware that never matched the board properly. Front panel connectors are small, easy to overlook, and responsible for an amazing number of preventable support calls. These are the wires that connect the case buttons, activity lights, front audio ports, and front USB ports to the system board. And while none of them seem dramatic on their own, a wrong connection here can make a brand new system appear dead, cause ports to fail, or leave the user convinced that major hardware is broken. Technicians work slowly with these connectors because the labels are small, the header pins are dense, and the consequences of guessing can range from a simple non-working power light to a system that never responds when the front power button is pressed. This is why experienced builders read the board diagram carefully, double-check orientation where it matters, and resist the urge to force any tiny plug into a nearby header that merely looks convenient, because front panel mistakes are rarely dramatic disasters, but are very often the hidden cause of embarrassing wasted time. Matching the board to the case is about far more than whether the board fits inside the metal box. The technician is also checking whether the mounting points line up with the case standoffs, whether the rear ports align correctly with the back opening, whether the case has enough space for the planned cooler and expansion cards, and whether internal drive cages or cables will crowd the board once everything is installed. A board that physically enters the case but does not line up correctly can flex under pressure, short against the chassis, or make it impossible to secure the board safely. And those are the kinds of problems that can quietly damage hardware long before the user understands what went wrong. Careful installation means treating the case as part of the compatibility equation, not as a neutral shell, because the motherboard, case, cooling, and cable paths all influence one another, and ignoring that relationship is how technicians turn a simple board replacement into a noisy, hot, unreliable system that is difficult to support later. Another important compatibility layer lives in the board firmware, which is the low-level software that helps the system recognize hardware and begin the startup process. Older discussions often refer to the Basic Input-Output System, BIOS, while most current systems use Unified Extensible Firmware Interface, UEFI, and a technician needs to know that these settings and firmware versions can affect processor support, storage recognition, startup behavior, and security features. Even in a hardware-focused task, the board is never just a physical object, because a correctly installed system board may still behave like a bad board if the firmware is outdated, a startup option is wrong, or a device the user expects to see has been disabled. Beginners sometimes assume that once every cable is attached, the job is finished, but technicians understand that installation includes preparing the platform to recognize the connected hardware properly, which is why they verify firmware compatibility, clear startup assumptions, and avoid declaring a board defective before ruling out a simple configuration issue. Many classic motherboard support mistakes come from treating one matching detail as if it proves total compatibility. A person may see that the processor socket fits and forget to check the case size, or may confirm that the board mounts in the case, but forget to verify memory type, rear port needs, front panel headers, or power connections. Another common failure happens when someone orders a replacement board based only on brand or model family, not on the exact features the system requires, and then discovers too late that there are fewer storage ports, fewer display outputs, or no header support for the front case connections the user depends on every day. Technicians avoid these traps by thinking in layers, beginning with physical fit, moving to electrical support, then checking built-in features, and finally confirming whether the surrounding hardware and the user's needs make the board a practical choice rather than merely a technically possible one. Before a technician installs or orders a system board, there is usually a quiet reasoning process that saves money and prevents rework. They look at the existing case, power supply, processor, memory, storage, cooling needs, front panel cabling, rear port expectations, and future upgrade plans, and they ask whether the new board supports the whole picture rather than just the one failed part. In a small business office computer, that may mean prioritizing dependable onboard video support, enough rear USB connections for daily peripherals, and a board size that matches the original case, so the repair stays simple and predictable. In a more specialized system, the thought process may shift toward expansion room, stronger cooling support, additional storage options, or a layout that keeps service access easy, but the guiding idea remains the same, because correct motherboard work is rarely about guessing what might function and is much more about eliminating mismatch before hardware is ever unpacked and installed. A useful way to think about system board work is to remember that technicians are not just replacing a part, they are protecting the stability of the whole platform. When the board is chosen well, installed cleanly, powered correctly, and matched to the case and supporting hardware, the rest of the system has a fair chance to operate normally and remain supportable over time. When the board is chosen badly, even a machine that appears to work on the first day may become the kind of computer that produces strange startup behavior, unreliable front ports, random shutdowns, poor upgrade paths, and confusing repair costs that make users lose confidence in the device and in the technician. That is why experienced support professionals respect the motherboard so much, because it is one of the few components where a single wrong assumption can multiply into several different symptoms that look unrelated until someone steps back and checks the board choice itself. By the end of this topic, the motherboard should feel less like a mysterious slab of circuitry and more like the decision point that shapes the rest of the computer. Form factor tells you whether the board belongs in the case. Onboard features tell you what the system can do without extra parts. Front panel headers determine whether the case controls and ports actually work, and compatibility checks with power, processor, memory, storage, and cooling tell you whether the whole machine will be stable after installation. Technicians who build or replace boards successfully are not relying on luck or brand familiarity, and they are certainly not assuming that close enough is good enough when connectors and standards look similar. They slow down, read the board, match the supporting hardware, and think ahead to how the machine will behave after the first boot. Because the easiest way to avoid expensive support mistakes is to treat the system board as the foundation of the entire repair and make every other hardware decision in relation to it.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.